It's pretty clear. Maybe you want to press, okay. Cool. Good morning, everyone. Great to see you all. We're happy to have Beatriz Moya here today and tomorrow visiting CWI. So Beatriz, you got her MSc and PhD for mechanical engineering at the University of Zaragoza in Spain, cum laude, and then you have worked as a postdoc in France, in Spain, and now you are at Singapore as a research fellow at CNRS. They have their department in the CREATE Tower in Singapore. And today you're going to talk about part of your work, which is about model order reduction, data-driven simulation. So please, the floor is yours.
Thank you very much. And thank you very much for coming to this talk. I hope you enjoy it. As Benjamin said, I'm going to introduce you a bit how in our group we work with learning biases and geometric biases applied to model order reduction and simulation. First, I would like to introduce a bit where I am working right now, because I work in Singapore, and discussing with Benjamin, I realized that this project is not widely known. So the government of Singapore decided to invest in engineering research to develop the smart city paradigm. And it invited several laboratories around the world to meet in one tower in the NUS campus in Singapore. And we are Berkeley, Cambridge, the ETH Center, MIT, and CNRS, which is the French National Research Center. And we work on different projects, but there are several projects in which we are working on collaborations. For example, in my case, I am a postdoc working with ETH also on structural health monitoring right now. And I belong to the so-called DECAG program, which is in hybrid modeling. We are 9 work packages discussing about AI, the role of AI in society, also for the smart city paradigm, but we are several work packages also in humanities, data science, of course, social sciences, law regulations, to study the problem of data-driven modeling and hybrid modeling from different perspectives. And personally, I work on the development of digital twins that are replicas of real phenomena. It can be a process, it can be an object, it can be a whole production line, a really big building. And we do that. We do this modeling to do prognosis and diagnosis. In other words, to perform the simulation of the behavior, especially under extreme events right now, we are focusing on that. And the diagnosis, if there is a failure, how we can recover the functioning of the system. For that, we mainly apply 3 different steps. The first one is reduction. We simplify the problem so that we can perform the simulation in real time and have the answers when we need them on time to do the critical decision making. Then the simulation, modeling of real phenomena to obtain an outcome that we can trust. And the final step is visualization, represent the solution in a way that a user that is maybe not an engineer or not a scientist can interpret to take a decision. So our desired characteristics for the digital twin are the trustworthiness, the real-time performance, and the interpretability of the results. So we propose combining data with knowledge. We can sort of distinguishing these 2 paradigms now in machine learning and deep learning that are the data-driven one and the knowledge-driven. We can simply rely on data. We have a great amount of data and we fit a model that is a black box. It can work, but we don't know what it means. We don't know how to interpret the results or which are the patterns that it is actually learning. It is a bit the way that Kepler learned the laws of planetary motions. However, we know we have a really good foundation of knowledge about several physical phenomena. For example, Newton developed this or reached the same outcome as Kepler based on the laws of mechanics. However, we are going to work in the hybrid paradigm, explaining more with less, that is combining both the knowledge and the data. We have some knowledge, but it may not fit the reality perfectly well. There's a gap. We are going to fit it with data. By combining both, we are going to trigger the robustness and explainability of the model. So if we compare how a human and how a machine learns from data, a human just takes the data, processes it, and has an outcome, a result. And we are really good machines at predicting things of real life. But it's because since we are born, we process tons and tons of data. There is an amount of information that a machine cannot do nowadays, in spite of the advances of informatics. So for a machine, we have the data, not as much as we have personally, and we have to define some other restrictions. For example, the task formulation, we have to specify what we want to do. Some assumptions that we may know about the problem. We have to design the network, for example, in the case of using neural networks or the machine learning algorithm that fits better the application that we are trying to develop, the initialization, and the learning rules. And then we process it and we expect to obtain the same result or even better, an augmented result compared to the ones that we obtain with our human mind. In this talk, we are going to focus on the assumption and network design, because this can be influenced by biases. What is a bias? A bias is a restriction in the learning process. We as people have several biases that influence our opinions, our decisions. In the case of simulation and model-ordered reduction, we are going to use these biases for the good, for imposing some knowledge that we have about the problem and alleviate the requirements and the reliance on the data that we have. So there are several ways of classifying the biases applied to machine learning, deep learning in general. But talking about simulation and model-ordered reduction, we mainly have these three types. The observational bias, that are the characteristics that data has and that will be acquired by the model. Our data, for example, can have some noise biases, and the network or the machine learning technique that we use will inherit these characteristics. The second one is the inductive bias. The inductive bias is a constraint that we impose in the architecture. That's why it is called a hard constraint, because it compulsory applies on the learning. And the third one is the learning bias, which is a penalty based on some knowledge that we have about the problem. Let's say, for example, the conservation of energy, symmetries, invariances, first principles in general, or if we know that we have to fulfill the Navier-Stokes equations. And this is a soft constraint because it is a penalty. We want to reach this ideal zero, but we are going to approximate in the optimization. And which is the effect of the biases? If we consider an initial point that has a great error in the optimization process, we can go, well, we are going to tend to go to the blue area, that is the one with less error, right? But if we leave it free, we will reach a minimum that is a relative minimum, but it's not the one in which we are interested. It probably doesn't fulfill the physics. However, if we impose some other biases, we will reach and approximate to the target point that is the one that we can interpret. With this in mind, I'm going to present three different applications of biases. The first one is the application of thermodynamic biases. This is going to be a learning bias, a soft constraint in which we are going to impose the laws of the thermodynamics. The second part is going to be dedicated to analyze the use of geometric deep learning, which is a hard constraint into the learning process, in this case of model order reduction. And in the third part, we are going to see the outcome of the combination of these two biases. So first, the thermodynamics into machine learning. We are going to perform simulation of real phenomena, and we are going to approximate the evolution of dynamical systems, defining the rate of change of a set of state variables that define our system in which we are interested with a mapping F. There are several ways of defining this mapping. We are going to focus on energetic approaches. For example, one way could be applying Hamiltonian dynamics, where we have this conservative bracket. It says that the evolution of the system is described by the evolution of energy of the system. The problem is that this applies to Hamiltonian system, which are conservative. The problem is that many processes and phenomena in real life are not ideal and conservative. They are dissipative because there are a lot of sources of error. So we propose a framework, a metriplectic framework, that describes the evolution of the system of a set of the state variables, taking into account two contributions: the reversible contribution, the one based on energy, and the irreversible contribution based on the evolution of entropy. And this is called the generic formalism, that is a coarse-grained description of non-equilibrium systems with regard to the evolution of energy and entropy of the system. This is a scheme that fulfills the first and second laws of the thermodynamics based on two types of restrictions. First of all, L and M, there are matrix operators in the description of the two brackets, of the dissipative and conservative brackets, must be skew-symmetric and symmetric posit-definite. We are going to impose it in a hard way in our learning scheme. And the second one is the fulfillment of the degeneracy conditions that say that the entropy does not affect the conservation of energy, and that the entropy does not affect the conservation of energy, and that the energy does not affect the dissipation, in a nutshell. With these two restrictions that we are going to pose in the learning formalism, we are going to fulfill both the energy conservation and entropy generation. However, we have to treat our problem as a discretized one in time, and we apply a forward Euler scheme to do so. We could apply some other integration schemes, but we decided to use this one. No. Also, apart from discretizing the learning scheme, we have to discretize the gradients of energy and entropy of the system. And the problem results in an optimization one, where we have to learn the operators. If we are working in a high dimensional space, we probably know the shape of L and M, and we shouldn't need to learn them, and only stick to learning the energy and entropy vectors, the gradients, sorry. However, if we decide to work in a low-dimensional manifold, there we have no idea of the shape of L and M. Working in a low-dimensional manifold is related to model order reduction, as I will show now. So this is our learning scheme. We are going to use a deep neural network that is called a structure-preserving neural network. We have a description of the dynamical system at time t. We don't use a random selection of state variables to have a generic formalism. We have to select the specific state variables that describe the evolution of energy and entropy of the system. For example, in the case of fluids, we need position, velocity, internal energy, which is going to be a problem if we have to interact with real systems because we cannot measure it. And in the case of having non-Newtonian fluids, the stresses. So we have our state vector at time t. We process it with a neural network that learns the mapping from the state to the correspondent energy and entropy gradients and the LNM operators. With that information, that's called learned simulation, because we are not learning the final outcome in time t+1. We are learning the operators of the equation to perform the time integration. So we have applied this formalism to several problems, but I'm going to show you one in which I did my PhD, that is the perception of liquids. That is a task that is so easy for us in our daily life and that we actually learn to do when we are just 2 years old. It's a super complicated task for robotics, especially when we are trying to develop this general artificial intelligence in which robotics have to learn or should learn how to interact with reality in an independent manner. However, we cannot propose a black box system to perform this perception. We have to introduce some physics so they know actually how to interact with the environment. To understand what we are going to do, we have to break into parts the different components of physics perception. On one hand, we have seeing, learning to perceive. We have some information coming from the scene, and we need to understand which is actually the physical state of the system. But we will have partial measurements because we only have a stereo camera that perceives the movement of the free surface. So here we have a first challenge. The second part, we have to perform a dynamical simulation in real time because the robot, for example, needs to have this information on time and perform a prediction. And what happens if our prediction doesn't match the reality? Because we have, for example, a new liquid. We need to learn how to fill that gap of the model and the knowledge that the model and the reality we are perceiving. This is the system incorporated to our model. We have a stereo camera. This is the general setting to learn how to perceive from images, and a glass full of a liquid. With this camera, we only have access to tracking the free surface of the fluid. And with only that information, we should be able to predict the next step of the fluid and perform correction in case we want to learn from it. So, as I've been mentioning, these are the challenges. First, performing fun simulation, because we need this real-time performance. Secondly, the partial measurements. We need to learn the actual state of the system. We propose to learn it from the history. And the third one is performing model adaptation and correction.
May I ask a question?
Yes.
So you say that you want to predict, or that's also then to predict the state of fluids. Do you mean so the entire fluid or the surface of it?
So in general, from a robotic perspective, they are mainly interested in the free surface. However, we are going to propose the prediction of the full reconstruction of the liquid. So the full volume. Yeah, the actual volume, because we may have information. Well, if we have information of the free surface and the container, we can obtain the volume. So we propose a scheme to also reconstruct the full volume, as I will show next, and also output some additional variables that we cannot measure or see with our eyes, such as the velocity fields and the stresses.
Okay.
Yes. So this is how the perception system is going to work. We have a high dimensional space in which our fluid lives, because we are going to discretize the volume into particles based on the smooth particle hydrodynamics theory. But we cannot perform the learning and the simulations in this state. We need to learn a reduced representation of the dynamics. For that, we need a mapping that goes from the high dimensional system to the low dimensional system and back to the high dimensional system. So this is two mappings, and then a learning algorithm to perform the time integration. And this is the learning scheme in a nutshell. First, we are going to learn this reduced representation of the dynamics of the fluid. And we are going to use a full scheme based on deep neural networks. It could be done with other techniques that we have actually employed, but in this case, we decided to stick to deep neural networks to have regularity in the techniques that we employ, and especially because here at the end, we need these recurrent neural networks. But well, in the first step, we apply autoencoders that are structures in deep learning that are used to find reduced representations of the dynamics. I will explain it now. Once we have trained the autoencoder and have this reduced representation, we learn the simulation engine in the low-dimensional manifold. And in the last step, we are going to substitute the mapping from the high-dimensional manifold to the low-dimensional manifold with a recurrent neural network, because we hypothesize with the fact that maybe from one snapshot of the free surface, we cannot reconstruct the full state of the dynamics of the system. However, by understanding the pattern of the movement that is present in the history, we can recover that information. So first, the autoencoder is a structure that is based on these two blocks, the encoder and decoder, both deep neural network architectures to learn a mapping from the high-dimensional manifold to the low representation, reduced representation, and then back to the high-dimensional representation. Here, we could apply several restrictions in the bottleneck. For example, we could impose orthogonality to approximate to POD, that is a linear model order reduction method. In this case, or some others. In this case, we just applied regularization, a penalization based on a L1 norm to impose sparsity, to approximate to the way POD works. Because for those that haven't used POD, in POD, we study the modes of the system, of the data that we have, and they are related to the quantity of energy, the quantity of information they preserve, right? So in a neural network, we usually have to impose a certain number of neurons, but here we want to leave the neural network to learn which are the modes that are not redundant in a similar way to POD. As I said, we are going to substitute the mapping from the high-dimensional manifold to the reduced space with a recurrent neural network. In this case, we decided to use a gated recurrent unit that is more complicated than vanilla neural networks, but simpler than LSTMs. In this case, we have less flows of information, and for simpler problems, it is better to not overcomplicate in general the architectures. It has an update gate, a reset gate, and an output gate. Everything dedicated to learn in the hidden space which are the features of the history. If we don't reset, we may learn short dependencies of data, and if we don't update, we don't learn new dependencies that arise from new sequences. Yes.
Sorry for interrupting. How are these neural networks trained there? Like, what is the loss function in this case?
Yes, in this case, the loss function is, instead of connecting this, the recurrent neural network to the high-dimensional manifold, we directly, actually, really, thank you very much. We find a mapping from these partial measurements from the sequences to the low-dimensional manifold that we learned previously, because here we have compressed all the information about the physics. So that alleviates a lot the computational cost, because if we have to learn a mapping to the high-dimensional manifold, it will be quite inefficient. So here the loss is simply the mean squared error and L2 norm to evaluate if we, because here, let me say, yeah, because it is important. Although afterwards we are going to use real sequences of data, first we are training the algorithm with computational simulations that approximate well the real behavior of the fluid. In this case, we are training first on glycerin, and we have, although here I show the pictures of a real glass full of glycerin, here you have to imagine that you have the free surface and the sequences of a computational fluid. And we know that the last snapshot of the computational simulation corresponds to a specific vector in the low dimensional manifold, and that's the loss. So it is a mean squared error based on, I have a sequence and I know that the last snapshot of the sequence corresponds to a specific state of the physics. So we learn that mapping. Yes?
Excuse me, your high dimensional data are the camera images that represent the surface of the fluid?
No, the high dimensional data is, I'm going back. It's this. It is the
So
fluid volume.
how do you get that? Do you have a suspension within your fluid that the camera can see these dots?
No,
Or is this really from a computational
discretization that
technique?
this is a discretization that I'm imposing internally. Then in the fluid, I track when I have to apply to the real liquid, I track the free surface.
Yes.
But the real representation of the fluid that I use internally is the reconstruction of the fluid volume discretized into particles.
Including the velocities of those
Yes,
particles?
velocities and internal
Okay,
energy.
so you assume that you have complete knowledge of the velocity state of the
Yes.
fluids.
When I train the networks with the computational simulations.
Yes.
Then all this network is to be exported to a real setting where we only have the partial measurements of the free surface.
Okay.
And from there, reconstruct the fluid volume. So from here, I can, with some techniques, extract the free surface.
Yes.
And I would have information equivalent to the one that I obtained from the camera. Yes. Yes.
So you have this inverse mapping, right? Z of say. What can you say about it? The inverse mapping from low dimensional space to the high dimensional space is not going to be surjective, right?
Sorry, I didn't.
This inverse mapping
Yes.
from low dimensional space to high dimensional space is not going to be surjective, right? It's so there are going to be some points in the high dimensional space which cannot be reached from this inverse mapping. You get my
I'm not
point?
sure I know what you mean, but yeah, indeed, you mean that you reconstruct the fluid, the whole fluid volume, but you have to compare there with the free surface only, because you can again perform some transformations of the full fluid volume, extract the free surface, and compare it with the one of the camera. Do you know what I mean?
Yeah.
I'm answering your question.
Yeah.
If not, I continue. You sure?
Yeah, please continue.
Okay, if not, we can discuss later. Yes, so we perform some validation on a glass full of glycerin. We have the free surface with a sequence of free surface captured with the camera, and we perform the time estimation of the fluid. We perform the full reconstruction of the volume that matches with the, for example, this represents that we have a reconstruction of the fluid volume with a free surface, and it matches the one of the camera. This is the information we compare, and we have an additional estimation of velocity, internal energy, and stresses. We cannot evaluate from the camera that this is correct, but we are imposing the thermodynamics into learning. So we assume that the result is going to be thermodynamically consistent. And this represents the evolution of the gradients of energy and entropy of the system, showing that we fulfill the laws of the thermodynamics. The gradient of energy is around 0 numerically, and the gradient of entropy is always positive, ensuring that we produce entropy. And for the correction step, we have our model trained with glycerin, and we want to learn a new fluid. Instead of performing all this process, obtain computational data, train the model, and maybe perform some corrections, we assume that using the thermodynamics, we have learned some patterns of the fluid dynamics that are going to be very similar for all the liquids that we want to simulate or learn about. So we are going to apply transfer learning, that is taking the model that we have originally trained and combine it with a new data set to perform the correction. What we are doing is considering the network as a whole, the recurrent neural network, the simulation network, and the mapping back to the high-dimensional manifold. We freeze the majority of the layers and leave only the last ones to fine-tune to the new liquid, because we consider that the first layers, that are the ones that are trained first, have the real pattern of the fluid dynamics, and the last ones are like the fine-tuning to approximate to the liquid, to the specific characteristics of the liquid. So we do that. We only train over the last layer of the recurrent neural network and the last 2-3 layers of the structure preserving neural network. And we train with this loss function, evaluating the reconstruction of the free surface. Here we only have the free surface, so it is the information that we compare for the learning, and also ensuring that we are fulfilling the laws of the thermodynamics with the degeneracy conditions. And this is the example of how the reduced order space, where we have projected our information, is updated. We didn't expect a complete change, simply an update to accommodate to the new type of fluid. We have done that for water, blood computationally. No one was hurt, and butter. And this is a video that represents the results. So we have
liquid butter, I guess.
yes, yeah, melted butter.
In Singapore, it's liquid.
Yeah, yes. So we have this computational glass of glycerin, and we want to learn the behavior of some other fluids. As I said, we have our original simulation scheme and these recordings of, for example, this one is beer. And we have the liquid, and we track the free surface. And as I said, we perform the transfer learning to adapt to the new liquid. And I'm going to stop. This was a first computational test on beer, as we see before. Obviously, the behavior of glycerin doesn't match the one we expect having beer. It doesn't match in amplitude and frequency of the slosh. And after the correction, this is on a test simulation. It was trained with other simulations. It fits the free surface, the real motion of the liquid, considering that beer is less viscous than glycerin, so it is out of the range of motion of the liquid. And I'm going to first put the end of the video here to show you some tests with water. We reconstruct the volume and we match the behavior of the free surface. So it is already information that a robot could use to not spill out the liquid, also on beer, gazpacho, that is a traditional Spanish tomato soup. And then honey, that is way more viscous than glycerin. So I say everything on test, and the error on the reconstruction is under 3%. And not only that, also for new liquids, we have an estimation of the velocity fields, energy, and stresses. Again, we cannot measure that, but we have a physically consistent estimation of them in case we need this information.
So just the question, so do you get the data from the camera like every time step and you use that to improve the
Yeah.
prediction of the
Yes,
fluid model?
exactly.
Yeah.
Yeah. It is, here we considered that we had, but we only train over one sequence of data, and we use that sequence to enrich the model. We could have considered sampled in time, but in this case, we consider actually, the network is initially trained at a frequency of 200 hertz because it is the simulation rate. The time step is smaller for Abacus, but with the camera, we couldn't match that rate.
Right.
So for example, we have information sampled at a lower rate to perform the corrections. And once we have used this short sequence, we correct with sequences of 5 seconds. Once we correct with one sequence, we input new sequences of the same liquid, and it matches the reality already. Yes.
Yeah, so if I understand correctly, your only the last layers, initial and last layer, the encoder and decoder layers are being learned for transfer learning, or?
No, it is, going back. I can. Here. We consider this network, all the 4 parts as a whole, and we only train over the last layer
There,
of the
okay.
gated recurrent unit and the last 2-3 layers of the structure preserving neural network.
So in some sense, do you like get the Reynolds number of the fluid as one of the latent
some sort
variables?
of,
You
yes.
get that in some sense.
Yeah, it is. That's why the first layers of the neural networks usually learn the bigger.
Yeah, that's
patterns,
what
the
I
big
was,
picture.
that's what I
So
wanted
in
to
the last-
clarify. So if you do it towards the latent layer, that will learn the low dimension, the Reynolds number.
Exactly, yes. So the fine tuning in the end of the new liquid that we previously didn't see. Yes.
So this treatment is only for incompressible flows, incompressible liquid.
Yes, well, we only tried with incompressible flows. So I'm not going to dare to say that it can be applied to others, but I think I would say that it could work with compressible flows because of the generic formalism, because it is, how to say it? It can be applied to any type of a scenario because of the versatility of working with the energy and entropy of the system. So it has been applied to several types of flows. And although we haven't tried with compressible flows because we are working with traditional liquids, I think it could be applied. Yes. Have more questions?
Yeah,
Okay.
so I'm not sure if this is the right moment, but it kind of reminds me, so the scenario is, right, despite varying the liquid, the rest of the scenario is the same, right? It's the same glass and it's moved
Yeah, in this
in the same
case,
flat manner, so is your ultimate goal then to also, let's say, infer how large is the glass, what's being done to it from
yes,
the?
yeah, exactly. This was the first part of the work. And recently, some colleagues at the University of Zaragoza have been using graph neural networks to work with different shapes of fluids, of containers, different levels of filling the container to have more versatility
Yeah.
in the application of the method. Yeah, this, since it is a fully connected neural network, has limitations
Yeah.
to generalize. So yeah, now the ongoing work is expanding it to more shapes, more volume.
Non-transparent glass.
Yes. Yeah. The thing is that with the setting we had, we stick to a shape of glass and then a scenario because it's where the camera was placed.
Yeah,
Actually, I
yeah.
could have chosen a different scenario, but I stick to it. Yes.
So just to clarify, so in your case, the inputs are just the camera pictures.
Sorry?
In your case, the input is just the pictures of
Yes,
the piece
the
of glass.
pictures of the camera, yeah. It is color images that we change to black and white to detect the free surface, and from that we can extract from the gradient in the black and white image, we have the free surface.
And
And
it's
we
a
can-
stereo camera.
Yes, it is a stereo camera, so you can have the depth of a stereo camera is a camera with two cameras. So you can perform triangulation of the depth in the same way as you do with your eyes. That's why if you don't have one eye because reasons, you cannot detect well the depth. With this, you have the perception of the depth.
But if these pictures are segmented, sort of converted to black and white, does it assume that the surface of the liquid is flat? Because, well,
Not
or-
really, because of the discretization of the pixels in the image, it detects quite well that it is not flat. Actually, several approximations of control of sloshing dynamics assume a pendulum for the dynamics of the fluid and that the surface is flat. In this case, the surface is not, because you have these in the walls, no, because of the tension. So it is not flat.
But could it be slanted, let's say, in this direction, if you're looking at it?
Yeah. Yes, yeah. There are techniques. In this case, I didn't apply these segmentation techniques, but there are techniques to detect also if you have not only a frontal camera, but a front view, but one from
Yeah.
any other side. You can track the position of the camera perfectly well and also perform segmentation. The thing is that since most of the liquids had no texture and were actually transparent,
Yeah.
we focused on the simulation of the liquid.
Yeah.
But we are exploring also techniques to capture the behavior from the top. I remember a work by DeepMind and some others, and it's based on the reflection of the light to detect the 3D view of the surface. In this case, since the main information was in the 2D, we decided to stick to the 2D. But yeah, if you detect, for example, that you have a 3D movement, so for example, towards you, and you can interpolate the movements. Yes. Yeah.
So I guess in view of time, we also would like to
I'm
see
sorry.
the remaining of the presentation and
I-
the questions at the end. Yeah. Otherwise, you cannot finish your story.
I go fast. So another way of imposing biases is the geometric biases. Long story short, a few years ago, the group of Bronstein, Bruna Cohen, and Belit Chobit created the paradigm of geometric deep learning. That is a way of mathematically understand and develop any operation regardless of the structure that you are imposing into deep learning. And the main definition was defining a domain in which our data is expressed. Can be an image, for example, a graph, or a sequence. That's our physical domain, it is called. Then you have the signal domain, that is where you express the information, the state variables, for example, of the system, and then the operation. This is based on group theory, mathematics, and what it says is that the assumptions of the symmetry group must be imposed also in the definition of the functions that we are applying over the data. In the case of images and convolutional neural networks, in our symmetry group, we apply the translation invariance. In the case of having a sequence of data for recurrent neural networks, we have the time warping. And in the case of graphs, we have the permutation invariance. And in this case, we are going to focus in the use of graphs, because until now we have been using multi-layer perceptrons with everything connected with everything, but that's an inefficient way of computing information, because our information has a structure, has a geometry. So we are going to consider we know it, and we are going to describe operations on the nodes, taking into account this permutation invariance. We are going to use graph neural networks because we are going to apply model order reduction over unstructured domains. For example, meshes that are not regular, for example, to adapt to the domain. This is the general scheme of geometric deep learning. We have some possible encoders and decoders, a way of mapping the information to a new space, but that's not compulsory. The important part of geometric deep learning or of graph neural networks is the processor, in which we are incorporating information in a graph from the nodes and the edges. For example, let's think in a mesh, the nodes and the connections, and we input that to the processor with a pre-processing step or without it. So we have a first processing, an aggregation of the information of the edges to the nodes, and then a processing of the nodes, and that's repeated iteratively in a way that a node that is placed here might be related to a node that is here. If we compute several passes, the information from this node will reach this one. So in very complex problems where we usually need, or there is a correlation between this point and this point, with this type of system, we can account for the correlations. And how does this aggregation work? Because it is the core of graph neural networks. First, we have to the information of the surrounding nodes. We consider one node that is placed here, and it's going to receive nodes, for example, this one. It's going to receive information from the adjacent nodes. So in the first operation, we define how we perform the message. Usually we just describe it with a weight. We add a weight to the message. Then the aggregation. It is how we incorporate all that knowledge of the surrounding nodes. In this case, the ones in blue, because we are in the first pass. A typical aggregation function is a sum, but we could define one based on the problem. And the last one, and the last part is define an activation. We could apply a nonlinear activation function based on the knowledge that we have of the problem to do the final step of aggregation. And once we have done this, this is the updated state of the surrounding nodes. And we include this information in the processing of the actual node that we are studying. With the passes, what we are doing is sequentially reach the ones that weren't connected in the first place to our node. In the case of graph convolutional neural networks, the aggregation function is defined with a kernel, where the state of the surrounding nodes is weighted with a set of weights, and it is summed with a kernel that is computed based on a mean and covariance matrix that is learned in the training process. This method is described in this reference. It is the MONET, and it is the one that we chose in our application, but there are several ways of perform the aggregation depending on the problem that we are studying. And we have applied these techniques to model order reduction on unstructured domains. So as I mentioned before, in a deep learning setting, we have two mappings. One from the high dimensional space to the low dimensional space, and another one from the low dimensional space to the high dimensional space. And we define that with graphs based on this convolutional aggregation. On top of that, we are going to relate the low dimensional manifold with a set of parameters that describe the high dimensional manifold. So the loss function of our neural network architecture is the mean squared error of the reconstruction of the high dimensional manifold, and also the one of the mapping. And this is a work we published with Professors Picky and Heishaven, and we applied to several problems, but I'm going to show you one related to bifurcation, because the goal of using graph neural networks was, on one hand, to work over unstructured and complex domains, and another one was to profit from this knowledge of the geometry of the problem to overcome several problems that can have applications like the one of bifurcation. It is really difficult to learn low-dimensional manifolds of bifurcation, which is, for those that are not familiar with it, when you reach a combination of parameters. In this case, we have the width of the inlet and the kinetic viscosity, in which instead of having a straight flow, that is what we expect, we reach a bifurcation point that approximates. Bifurcation, for example, in an structure would be an alternative when we are loading a structure. If we are applying a load, for example, when we reach an alternative stable point that will cause the structure to collapse, for example. That's why it's so important to understand bifurcation in this case of fluids. And here we only used 10% of data because of the geometric priors, because it was able to understand the patterns of the bifurcation with less data. And actually the low dimensional manifold is highly interpretable because we perform clustering and it detects perfectly well the region where we have the bifurcation, these two stable points, and the region where we only have the ordinary solution, the unique solution. And the combination of biases, I'm going to show how we combined the graph neural networks with the thermodynamics-informed neural networks. As I said, this is our main block, and we can use the mapping to another, these pre-processing mappings and post-processing mappings. In this case, we have the state of our liquid system, dynamical system, and we split the information into the one that is associated with the edges, for example, the position. The position is associated to the edges, and the rest of the state variables, the velocities, the stresses, is in the nodes. We perform encoding of these two and perform a simple aggregation with summation processing. And in the decoder, we obtain, as before, the L and M operators and the energy and entropy. And this is a change with respect to the previous approach, because in this way, by learning entropy and energy and perform differentiation to obtain the gradients, we ensure that the existence of energy and entropy of the system. This is the results of my colleague Kirkus, but I decided to show them because they show really well the performance of the method. As you can see, the energy is close to constant. We know that in neural networks, it's really difficult to reach that zero, especially if it's a soft constraint, and that the entropy is produced. If we compare the errors of the different architectures, we had this consistency in the SPNN, the structure preserving neural network, but we weren't using the geometric information of the problem. We were connecting everything with everything. And as I said, it can be really inefficient. Only changing to graph neural networks, the result was better. The problem is that the error was high and not interpretable. With the last combination of biases of graphs and physics, we have the lowest error, demonstrating that the combination of biases is highly desirable. And this is one of the last examples in which we've been working, and it is the snap-through, which is really difficult to predict because it is unstable. You reach an unstable point and you have a drastic change of shape. As you can see, in this case, the load is the voltage. And with traditional methods, it's really difficult to predict. There are techniques based on bifurcation theory to estimate the loads and the vibration and the modes, but still it is complicated. So we decided to use this thermodynamic framework based on graphs because the snap-through is related to the energetical state of the system. And these are the results. We have a shell in which we applied several loads and we predict the behavior of the snap-through. It is worth noting that we consider several shapes although it is regular, we consider several shapes of shells, and we only consider that we applied the load in a certain number of nodes, not in the whole shell. So the predictor is learning a completely unknown case in terms of position of the load and shape of the shell. We have implemented it also with immersive technologies, especially the glasses and the gloves, to detect this force and interact with the augmented reality that is physically consistent. And we are exporting this technology also to real pieces for the car industry. So in our conclusions, incorporating knowledge triggers the interpretability, efficiency, and robustness, and also trustworthiness of the results. We obtain better accuracy with less data, and this is desirable in the smart data paradigm because we not always have all the data that we desire to reach this high interpretability. But sometimes the more knowledge is not the better, because imposing more biases and more restrictions could difficult the training of the networks. And for example, in this case, in the paper I show you, we analyze how it could be better to learn from only one bracket instead of two, for example, because in the generic formalism, we have these two brackets for energy and entropy evolution. In this formalism, they are combined, and it is more efficient in terms of training. And in future research lines, we are working on including physics in the aggregation functions, because sometimes we know laws about the materials that can be incorporated in that in that aggregation function, giving more interpretability to the operations. Also, everything that I showed was deterministic, so it was enough for now. But if we have to take the decision with the information that we have to include the stochasticity and the uncertainty quantification to evaluate if we actually can use that information. And in the last part, we are also working on reconstructing not only from partial measurements of the physical state, but also a sparse use of sensors, for example, in super resolution of liquids. And I want to acknowledge the support of the Spanish Ministry of Science and the Ministry of Digital Transformation and Civil Service, because with it was possible to do this research, and also to the DECAG program and the National Research Foundation in Singapore, and to my team always. We have to acknowledge always the people we work with, because it's the most important part of research. And that's all. If you have more questions, and thank you very much for listening.
If there were still questions, Jonas.
Yeah, just a question. So you mentioned that you track the surface basically only from one viewing angle, right? So that it's mostly, let's say, the motion in well, one
Yes.
kind of plane. So why immediately go for this smoothed particle hydrodynamics in 3D and not for something like shallow water equations or something like that, where you kind of reduce the dimensionality of the physical problem as well?
Yes, the motivation was thinking about the future, because now we are expanding it to graph neural networks and adapting to new shapes of containers and new volumes of liquid. And in using the theory of the smooth particle hydrodynamics from the beginning was the way of setting the foundation for the future developments. That's why we decided to use it. And it's what we discussed, that it is true that we focused on, although it is a 3D volume, it is a 2D movement. But the goal is also to use the camera from any angle and detect the free surface from any angle, complicating the problem. I don't know if it answers.
Yeah. But I guess it's still interesting then to compare a bit like how easy different, say, physical models are to
Yes.
learn, basically, right?
Yes,
So
I
yeah.
agree. Also, because the smooth particle hydrodynamics has a really strong foundation for the generic formalism. That was the theory that we decided to use also to perform the correction a posteriori, right? Because when the lack of knowledge arises, we have this increase of entropy. So we saw that it was a good fit from a thermodynamic and energetic point of view.
I wonder about some parameters of the middle part of your talk, the turbulent flow in the pipe with the
Yes.
inlets. So you go from the complete data down to your reduced description. How many variables do you have there?
Now I don't remember exactly. I think it was 10.
Okay, so and
It
in
was a
those,
great reduction.
so your vector Z would have approximately 10 components
In the low dimensional manifold,
in the low
yes.
dimensional manifold, yes.
Yes.
And then in the description in terms of those variables, both the energy function and the entropy function and the matrices L and M are unknown. So you have to learn all four of those. You're going to do the evolution in terms of these 10 variables, I think.
Because you are talking about the fluid, the sloshing
Yes.
fluid. Oh, sorry, because I was
No,
thinking
not
about
the flow in the pipe.
the flow in the pipe. There, it is only model order reduction. There, we have not applied the generic formalism. We don't know.
Oh, I
we don't
thought
do
you showed,
simulation.
I thought you pointed also then to the Hamiltonian entropy formalism.
No. There we are not.
Okay.
We could apply the formalism to perform simulation, but in this specific case, we simply stick to model order reduction and mapping from a combination of parameters, being able to predict the reconstruction of the flow also in the bifurcating regime.
I see. Okay.
Yes, but in this case.
You were not doing the evolution.
No.
Okay.
No.
So maybe you can comment on how generic is the generic formalism and also why you sort of know for the full order models from physics perspective that generic makes sense, but you also apply it to the reduced order models,
Yes.
right? So what is the argument for doing that? Or maybe I could also rephrase, are there models that don't fit in generic?
To my knowledge, every model fits in the generic formalism. What can I say? To my knowledge, yeah, everything we proposed and we studied in the literature works for generic. It has been applied to complex fluids, complex materials with high nonlinearities, because using energy and entropy is in general quite general, right? But in the end, it is a coarse description of the dynamics. Why we use it in the low dimensional manifold? Because in the assumptions, we consider that if we go to the low dimensional manifold, we are increasing it is the same information, the same patterns, but we are increasing the entropy because we are applying this reduction. So I must say that I don't remember the physical axioms that support all the mapping, but the basic idea is we have the same patterns and we are just increasing the entropy in the reduction. Hence, we can apply generic in the low dimensional manifold. Obviously, in the low dimensional manifold, we don't know the variables. They don't have a physical meaning, but since we learned the low dimensional manifold from, in the case of fluids, from velocity, position, energies, and in the case it's necessary stresses, we assume that the information of the physics of the dynamical state, it is there compressed. It is new variables that don't have a physical meaning, but they have the information of this original state. So we can impose generic there.
In the beginning, you also said that for digital twins, it would be nice to have something like explainability.
Yeah.
So have you looked at what the latent variables represent, and maybe there is some physical meaning?
To what we saw, they are related to the slosh, to the amplitude of the slosh. It represents somehow the I talk in my case, for example, you can see some patterns of the amplitude and the frequency of the slosh of the original data set in the high dimensional space. The final goal, because talking with Professor Gremela, that is really involved right now in using the generic, it is one of the people that developed the generic formalism. They have been working on the study of neural networks in combination with generic, and one of the goals is to apply generic to go from the high dimensional manifold to the low dimensional manifold and have this additional interpretability. So far, we haven't applied any restriction to go further.
Any other question? Okay, let's thank Beatriz once more. We're going to have lunch. I guess we just go to the matrix. So if you want to join, then feel free.